Isolation forest has quickly become a staple in anomaly detection systems. Its main advantage is being able to find complex anomalies in large datasets with many features. But when it comes to explaining those anomalies, these advantages quickly become weaknesses. To take action on an anomaly, we often have to understand why it was classified as one. Unfortunately, with isolation forests, these reasons are hidden within the complex model structure. So, to uncover them, we turn to SHaP. Using Python, we're going to apply SHaP and explain how you can interpret its output. Even though isolation forest is an unsupervised model, we can see that we can still use SHaP to explain its output. That is to understand how features have contributed to the scores of individual instances, as well as which features are important in general. On the more technical side, we will discuss considerations around using KernelSHAP versus TreeSHAP and how the interpretations of the plots change. Okay, so before we start, I'd also just like to mention that I have a course out on SHaP. It covers all of the theory as well as the Python code behind the method in a lot of depth. If you're interested in that, definitely check it out and wait until the end of the video where I'll explain how you can get it for free. So just a little bit of background information if you're not familiar. Anomaly detection involves identifying unusual instances that are not consistent with the rest of your dataset. This could involve flagging fraudulent transactions, finding faulty equipment, or detecting novel cyber attacks. Although they're all in different domains, all of these applications have one thing in common, and that's that they have no target variable. When detecting outliers, we often don't have a clear definition of what constitutes them beforehand. And to make matters worse, we often have to look for them amongst large datasets with many features. This is why isolation forest, an unsupervised tree-based method, has become so popular. So we're not going to go into too much depth around how the isolation forest works. I actually have an article that I wrote for DataCamp which covers the topic. So if you are interested in learning that theory, I will link to it in the description. So to get some sort of idea, I will summarize how it works. So the isolation forest is built on isolation trees, and it is a collection of isolation trees, just like a random forest is a collection of decision trees. So how you build one of these isolation trees is you start with all the features or all the instances in the root node, or a sample of the instances in the root node. In this case, we have a sample of 256 instances. Then the next step is you select one feature at random. And in this case, we have selected feature X. You then select a split value within this feature's range at random again. And now, then you just use that split value to divide the instances into two groups, where if the instance has a value less than that split value for feature X, it goes to the left-hand side, and if it's greater than the split value, it goes to the right-hand side. And then to complete the isolation tree, you just recursively repeat this step until all instances or all of the leaf nodes have one instance. And yeah, the idea there is that if a instance has a short path, then it is more likely to be an anomaly because it was easier to separate it from the rest of the data using this random split process. Okay, so that's one isolation tree. And obviously there's a little bit of randomness there. You could have a normal instance just by chance being split off quite early on. So that's why you need a collection of isolation trees, and you capture the average path length in the isolation forest. And yeah, how do we actually capture those average path lengths? Well, in the isolation forest, we use the Anomaly Score. And yeah, S is our anomaly score. And H of X is the path length of instance X in one of those isolation trees. Then EH of X is the average path length across all isolation trees. And finally, C of N is a normalization value. And we need this because if you have more instances in your tree, if you have a bigger sample, the tree is going to be bigger on average. And so the path lengths are just going to be larger for all instances. And yeah, I wouldn't be too worried about the maths here. The actual score calculated by the implementation that we'll use is slightly different. What's important to know is the anomaly score captures the average path length of an instance. And shorter path lengths suggest that that instance is an anomaly. Now, the next question is, how do we interpret the SHaP values for this model? Now, if you use SHaP, this plot will be very familiar to you. It is a waterfall plot. And in this case, f of x is our prediction. F of x is the average prediction across all instances. And the SHaP values are just all these values in between. And they tell us how each model feature has changed the prediction. So in this case, f of x is the model prediction. And so you might be asking, how can we calculate SHaP values when the isolation forest doesn't really have a prediction in the same sense as a predictive machine learning model? Well, the beauty of the SHaP algorithm is that we treat the model as a black box, and we permute the input and measure changes in the output of this black box. And that output doesn't necessarily have to be a prediction. So for isolation forest, f of x is simply the anomaly score. And so we interpret the SHaP values as the contribution of each model feature to the anomaly score when compared to the average anomaly score across all instances. And as we'll see when we use TreeSHAP, f of x actually defaults to simply the average path length. And yeah, we'll discuss that a little bit more in depth when we get to that section. Okay, with all that theory behind us, let's jump to the notebook. So we're working in the isolation forest notebook in the additional resources folder. And I will link to the code in the description. To start, we have all of our imports, and yeah, there's some very sort of standard Python imports. We obviously using the SHaP package and using isolation forest from scikit-learn. And finally, we are going to load our dataset directly from the UCI machine learning repo. And just for your interest, this last little bit of code here, that's so that the SHaP plots are displayed with a white background in VS Code. So yeah, then we're going to load our data set directly from UCI, and this will take a little bit of time. So the data set's loaded, and we simply just print the variables, which gives us a kind of a description of the data set. And we're working with a power consumption data set. And this is actually a time series data set. And in this tutorial, we're not going to treat it as a time series data set, which yeah, just keep that in mind. So it contains features like global active power, which is the total power consumption at the time the reading was taken, and also things like the sub-meter readings, which are the power consumptions of sort of individual rooms or sets of appliances in this household. So the next step is to do a little bit of data cleaning. And in this case, we're just sort of dropping all the missing values. So we start by selecting our data or getting our data set. We then convert the date or format the date and select all of our features. So if you take a look at this data set, you'll notice that the missing values are actually encoded as question marks. So this line kind of just converts all of those to NaN values. We're saying, essentially all non-numeric values will just be replaced by NaN. And then we drop all of those NaN values. And now that might not be the best practice when you're doing anomaly detection, because rows with a lot of missing values might actually be an indication that that instance is an anomaly. But in this case, we're just going to keep things simple and just keep that in mind when you're actually applying isolation forest. Then we are going to do some feature engineering. And like I said, we are dealing with the time series data set. So what we're going to do is for every date, we're going to take the mean and standard deviation of all the measurements in that day. And that will essentially give us one row for every day, and we just get like the mean throughout that day. And you can see the result of that is we have this data set below, and we have something like the mean global power consumption during that day, or the standard deviation of the power consumption, and also things like the mean of the individual room readings. Then the idea is that with these sort of 14 features, we are going to find days where these readings kind of look funny. And then we can go further investigate what happened on that day and why did we have anomalous meter readings. And also just to point out, we have 1,433 days in this data set. So the next step is to train our isolation forest. To do that, we first need to set a few hyperparameters. In this case, we have the number of trees, which are the number of individual isolation trees in the model. We also have our sample size and contamination value. Now, I go into a little bit more depth on these parameters in that article that I mentioned. But for contamination, what's important to know is this is the expected proportion of anomalies. And so in this case, we expect 2% of the days in our data set, or the readings, to be anomalous. And the implementation that we will use, the scikit-learn model, will automatically classify 2% of the anomalies or 2% of the instances as anomalies. So then the next step is kind of just to train the isolation forest. We select all of our features from that aggregation data set that I mentioned. We use those hyperparameters to initialize an isolation forest, and then we just use the features to train the isolation forest. And you'll notice that there's no target variable because, as I mentioned, isolation forest is an unsupervised algorithm. So once we have our model, there's a few useful functions that we can use. The first is this decision function, which will just calculate the anomaly score for each instance and predict will classify the instances as either normal or anomalous. And in this case, 1 indicates that it is a normal instance, and -1 indicates that it is an anomaly. And if you do the maths, you'll see that 2% of the instances have been classified as anomalies. Now, a final step before we get to our SHaP values is let's quickly just visualize all of these instances. So this plot is it's a scatter plot of the normal instances and the anomalous instances. And the idea with this one is that, can we see any patterns through time? And we actually can. You can see that there's these clusters around the beginning of the year where a lot of the readings seem to be anomalous. So perhaps there's some cyclical nature in our data set. And yeah, that can sort of help us explain at a higher level why we're getting these weird readings. But to get a deeper understanding of each of these instances, we are going to have to use SHAP. Now, what makes the most sense to me is to interpret the SHAP values in terms of this anomaly score. But as we'll see, it's not actually that straightforward. So because isolation forest is a tree-based method, I would have expected to be able to use the tree explainer with the isolation forest. But one problem is that the default output of the isolation forest is not actually the anomaly score. And we have to kind of explicitly tell SHAP that we want the decision function as the output score, which gives us that anomaly score. But yeah, the problem with that is when we try to use the decision function with tree explainer, we actually end up getting an error. And yeah, I think the reason for this has to do with the way that TreeSHAP has been implemented. It just can't make use of the tree-based structure of the model when we tell it to use the decision function. But not to worry, thankfully we can use KernelSHAP, which is the model agnostic implementation of the SHAP algorithm. And it should work with any model and any output. The problem is that KernelSHAP is a lot slower than TreeSHAP. And if we try to run it on all of our 1,400 instances, it's just going to take forever. So what I've done here is I've taken a sample of our instances, and specifically I took 100 random normal instances and all of our instances that have been classified as anomalies. So in total, we have 120 instances in our sample. And yeah, then we can use the exact same code as before. This time we're using the explainer function, which will use the KernelSHAP algorithm. And we're just passing in a sample of our features to this explainer object. And yeah, we can plot the SHAP plots just like for any machine learning model. And in this case, we are plotting the waterfall plot for our first instance, which was an anomaly. And you can see that when we look at f of x, which remember gives the anomaly score, and in this case it's less than 0. And so yeah, this instance has been classified as an anomaly. And looking at the waterfall plot, we can see which features have contributed the most to this anomaly score. So for example, the global active power consumption, which is the total power consumption, seems to be the most important feature for this specific anomaly. So the idea is that if we wanted to investigate this anomaly, we would probably be best to look at these sort of top features here to get a better idea for why this instance is being classified as an anomaly. And then just for your interests, we can also plot the waterfall plot for a normal instance. And in this case, f of x is greater than 0. And so yeah, it hasn't been classified as an anomaly. We can also plot our aggregations of SHAP values like the mean SHAP plot. In this one, we can see which features have contributed the most to anomaly scores in general. It doesn't really look like there's any feature that stands out. One caveat with this one is that because our data set is a little bit skewed, the SHAP values from the normal instances might be averaging out the SHAP values from the anomalies. So you might want to repeat this analysis by only calculating SHAP values for anomalies, and you might sort of see clearer patterns in this plot. A very useful plot is the B-swarm plot. This is a plot of all the individual SHAP values. The points are determined by that feature's value. And remember that anomaly scores less than 0 are an indication that it's an anomaly. And when the SHAP value is less than 0, this tells us that that feature has contributed to this negative anomaly score. And so if we want to sort of interpret this relationship for this first plot, it's saying that when the sub-meter readings are high, the SHAP values tend to be lower. So higher than average sub-meter readings indicate that the instance is an anomaly. Okay, so clearly we can get a lot out of SHAP using the KernelSHAP algorithm, but TreeSHAP still has a lot of benefits. It's much faster than KernelSHAP, and as you'll see, we'll be able to use SHAP interaction values. So it's worth also exploring how we can apply this algorithm to isolation forest. And to do that, we simply just insert the isolation forest model and let it use the default output. And yeah, as you can see, SHAP values for all 1,400 features are calculated in less than a second, so significantly faster. And that just allows us to analyze much more instances. And yeah, you can see we can plot an anomaly or plot the waterfall plot for an anomaly and for a normal instance. So in this case, you can see that, okay, the f of x value is lower for the anomaly and it's higher for the normal value. But what exactly are these numbers? And it's not actually that straightforward. It took me quite a while to figure it out. And I found the answer in a GitHub issue page, which is, yeah, if you're ever having a problem with SHAP, like GitHub is a very good resource. So what it actually is the path length of an instance, or the average path length across all of the isolation trees. And yeah, you can see that in this plot where I sort of get all of the path lengths from, I get the path lengths for the anomalies and for the normal instances. And you can see that just kind of on average, the average path lengths for the anomalies are lower than for the normal instances. And yeah, so the idea is that you can still use SHAP. Just keep in mind that the interpretations of the plots are different for when you are using KernelSHAP and when you are using TreeSHAP. And yeah, that interpretation might add some more complexities into any sort of presentation that you are doing, because now you sort of jump from explaining isolation forests using anomaly scores to using path lengths, and it just adds a little bit of complexity. But one other major advantage of using TreeSHAP is that we can calculate SHAP interaction values. And if you're not familiar, these kind of break down SHAP values into their main and joint contributions. So we can actually see which features sort of have contributed to the path lengths by themselves, but which have also sort of had a joint contribution together. And high joint contributions indicate that those features have influenced the anomaly scores or the path lengths through an interaction. And so we calculate the SHAP interaction values, and then this code simply plots a heat map of the average SHAP interaction values. And yeah, you can see sort of these main effects where there's sort of all of the features kind of contribute the same main effect. But then you can see one interaction standing out, and that's between the mean and the standard deviation of the submeter reading 2. And yeah, at this point I haven't really gone deeper in understanding why that is. So maybe you could reach out in the comments and give me any suggestions on why the mean and standard deviation of these features could be interacting. Yeah, if you sort of got a little bit confused towards the end with all these SHAP interaction values and stuff like that, like I mentioned, I have a SHAP course which covers all of these applications in much more detail. And if you're interested in that, I'm running a free promotion at the moment. You can use this coupon code to get free access, but it's only valid for the first 20 people. So yeah, jump on it while it lasts.